Before electron configurations can be written, we must first understand the atomic orbitals that are available to the electron. We'll begin with a brief discussion and explanation of wave mechanics. We will not solve wave equations here because this is not a calculus class. These equations are solved in an upper-level chemistry class. In our class, we only want to understand the meaning of these terms. Psi is called a wave function. The wave function is a function of the coordinates of the electron's position in three-dimensional space. This is necessary because we would like to have an idea of where the electron is around the nucleus. H is called an operator, which contains the mathematical terms that produce the total energy of the atom when applied to the wave function. E is the total energy of the atom, or the sum of the potential energy due to the attraction between the proton and the electron, and the kinetic energy of the moving electron. But the main takeaway from this slide is that the wave functions that satisfy the equation are called orbitals. In other words, there are multiple wave functions that fit this equation. This is common when working with wave functions in calculus. Also, notice how our definition of an orbital is different than you might expect. Here, an orbital is not an orbit, like the Earth revolving around the Sun. But rather, our orbital is a wave function that satisfies the wave equation. This is the mathematical explanation of the orbital. But what about the physical meaning? Physically, the orbital is the space somewhere around the nucleus where the electron is likely to be found. In calculus, squaring the wave function and integrating over all space gives the radial probability distribution. This is the probability of finding the electron some distance from the nucleus. The figure shown here is an example of a plot for the lowest energy wave function, or the lowest energy orbital called 1s. Here, the plot shows the probability of finding an electron versus distance from the nucleus. The highlighted area shows that the peak, or maximum radial probability, occurs at a distance of 5.29 times 10 to the negative 2 nanometers, or 0.529 angstroms from the nucleus. This means there is a 90% probability of finding an electron somewhere around 0.529 angstroms from the nucleus. Quantum numbers. These are a series of numbers that describe various properties of an orbital. A principal quantum number is labeled n, the angular momentum quantum number is labeled L, the magnetic quantum number is labeled m sub L. The principal quantum number has integral values starting with 1, and it's related to the size and energy of an orbital. As the value of n increases, the orbital becomes larger. The electron spends more time away from the nucleus. The energy increases since the electron is less tightly bound to the nucleus and farther away. The angular momentum quantum number, L, has integral values from 0 to n-1 for each value of n, and is related to the shape of the atomic orbitals. A value of L for each orbital is assigned a letter. The magnetic quantum number m sub L has integral values between L and negative L, which includes 0. M sub L is related to the orientation of an orbital in space relative to the other orbitals in the atom. More importantly, the number of answers tells how many orbitals exist. Here's a table of the quantum numbers for the first 4 levels of orbitals in the hydrogen atom. A separate video explains how to build this table from the quantum number rules. Let's review. N is the principal quantum number. It tells the size of the orbitals. L is the angular momentum and tells the shape of the orbitals. Each L has a letter associated with it, and thus the N-L combination gives the name of the orbital. M sub L is the magnetic quantum number, and the number of results gives the numbers of orbitals.